So now let's talk about marginal densities. We actually already talked about marginal densities because that's kind of the univariate case. It's what you call something a marginal density when you have a distribution over multiple random variables. So in this example, age and sex, but then you only calculate the density for one of them. So here's my population data set. It's a very small population. So I have 10 people in it. And to calculate the marginal density of age, I just count up every unique value of age and how many times it happens. And I divide by the total number of people in that population. So here, for example, there are 4 2-year-olds in this population. So the value of the density there is 4 over 10. I could do the same thing for sex. So this is what is called the marginal density of sex. And I've done the exact same thing, except now I'm counting unique values of sex instead of unique values of age. So here I get, there's 2F and 8M. Here, what I'm doing is showing that it's the same thing. Here, my population is very small, but if I have a really big population, it doesn't matter. You can still do the same thing, right? So in this giant population, I'm getting the density of age, and I'm getting the density of sex based on this population data set. So the marginal densities actually come from the joint density as well. So here I'm showing you from the population data set how to do this, right? What if you don't have the population data set? Of course, you never do, right? But what if somebody tells you, I think this is the joint density? How can you get the marginal density? Well, all you need to do is sum up the probabilities that correspond to the row in the marginal density. So what I mean by that is, like, let's say you want to know what is the density in the marginal density of age equal to, right? What is that? That's the fraction of 2-year-olds in the population. So if I want the total number of or the count of 2-year-olds in the population divided by the total population. So if I want to count how many 2-year-olds there are, I can split that into 2-year-olds that are female and 2-year-olds that are male, right? And then I get the total count of those, and I just add them together. So that's why you can get values in marginal densities from just adding up values in joint densities, and you don't need the population data set, right? Because you've already pre-counted within each group, and you just need to add the relevant groups together. Similarly for sex, right? If I want the marginal probability or density that somebody is male, I just need to add up all of the rows corresponding to M over here. So here I got 0.5. Notice that these numbers I got from the population data set, right? But you can see I could have gotten them from the joint density, because so here the number is 0.5, or 50%. Here I can get that by adding 5, 10 is 15, 15 is 30, 45, 50, right? So it's the same whether I go from the population data set or I just add up the numbers in the joint density. And the reason, again, it's just counting, right? So you can write it notationally as well, and it boils down to this addition rule from the last lecture, or total probability, which is if you want the total number of people where y equals y, that's the same as counting up within subgroups of x, right? The number of people where x is x and y is y, and then adding up those totals across the strata of x. And from this, you can get basically all I'm doing to go from here to densities is dividing by the population total on both sides. So you can also look at this in terms of some kind of visualization, right? If you have this heat map, if I want to get this is a 2D heat map. If I want to get the marginal density for one variable or the other, what I'm doing is I'm adding up the values of the joint densities along particular axes. So for example, what's the probability that somebody is 5 years old? Well, I need to get the probability. If I have the probability that somebody is 5 years old and male, and 5 years old and female, I just need to add those two probabilities. Similarly, for the probability that somebody is 3 years old, I need to add the two probabilities corresponding to age equals 3, right? So what I'm doing is I'm squishing this down in one axis to get this. And to get this, the probability that somebody is female, I need to add up all the probabilities in the female column, regardless of age. So I'm squishing it down like that, and summing. And this is actually why it's called marginal probability, because back in the day, people were actually writing out these two-dimensional densities of particular variables, and they were calculating the if you wrote that on your sheet of paper in the middle, then when you take the row sums, that ends up going in the margin of your piece of paper or the margin of your table, either the top margin or the side margin. So that's where we get marginal probability from. Let's go back to this problem here. So this is the same table as we looked at before. What we'd like to do is calculate the marginal densities of educational attainment for mothers and their children. That's the first part. And then secondly, do those densities make sense to you? And then thirdly, calculate a particular probability using the joint density, and then calculate it again using the marginal density. So let's have a shot at that. All right. So we're calculating the marginal density of both variables. So we'll do the marginal density of mother's education first. So what's the marginal density at x equals 1? It's just the sum of these values here. So I'm going to sum up all of these values. Let's just make a little table over here in the margin. And let's put that there. So here we have, let's do 18 and 12 is 30, and 16 is 46, and another 6 is 52, right? So this is going to be 0.52. And then down here, we have 9, and 9 is 18, and another 6 is 24, and then another 4.5 is 28.5. And then what do we got going on here? 10, and then 4. 0.14. And down here we have 4, 5.5. Oops. 0.55, like that. Okay. So this is the density of x. So this is a big X. This is a little x, which for a discrete random variable corresponds to the probability that big X takes the value little x. Okay. Let's do the marginal probability for y as well. Same thing. We're just adding up these values. So this way we get 10, 26, and 2, 28. And here we have 12, and 18 is 30, 31.5. This one, we have 21, and 5 is 26. And then here, we get 10, 14.5. Great. So that's this thing here is the marginal density of y. And these numbers in here represent this condition, or this joint density. Great. So do these marginal densities make sense to you? That's the next question. Well, so let's say this one represents the mother's education here. And what we're seeing is that something like half of all mothers have only high school education or less, right? And then some are only like 15% are going to college, and less than 1% are going to grad school. Here, for their children, we still have like a large portion of people either not graduating high school or only high school. But then we have over a quarter of people, and maybe like a whole third of people are going to college or higher. So it's more. And again, to me, that makes sense if you think about how things have changed over time, if these children are all 30 years old or older, then we're talking their mothers were probably growing up in a time where women getting higher education was less prevalent, and so that kind of tracks. Maybe it's a little too extreme, but it is at least plausible to me as a non-expert that this would be the distribution, and this also tracks with roughly, I think, the distribution of modern day educational attainment in the U.S., not stratified by sex or gender. So that kind of makes sense to me. And now the last question is to calculate a particular probability using both the joint and the marginal densities. So let's do that. So first I'm going to calculate this using the joint density. So here it's probability y is greater than 3. So we have y greater than. So that is only this, right? Y equals 4. It's not greater than or equal to, it's just y equals 4. And there's no condition on x. So that corresponds to all of these cells here. So we have to add these numbers together, and the number we'll get is 14.5%. Okay, and now we can also do it with the marginal density. So notice, because there's no x here, right? It's just the probability that y is greater than 3. We know we can get that. We can get that by adding together over the value of this marginal density over little y greater than 3. So in this case, that's just one value, which is y equals 4. So that sum is just summing over one value, so it's going to be equal to just the value of that density at 4, okay, which is this number here. And of course, it's that number there because number is precisely the sum of these numbers, right? But if the problem had been different, if this had been, let's say, y greater than or equal to 3, right? Then with the joint distribution, we would have gotten it by adding up all of these numbers in this bigger box, right? And then from the marginal distribution, we would have gotten it by adding up these two numbers, right? Okay, so that's enough of that problem. Let's talk again very briefly about continuous random variables and the relationship between the joint PDF, which we saw as like this kind of like 2D histogram, and how you get the marginal PDF. So if you have a joint PDF like this, we know that to calculate the probability that somebody is in, some kind of square or some region on the XY plane, what we have to do is draw that region and then take the area under that, or the total volume under that curve. And that's kind of like the count of the total number of people who are standing there, right? So if we're doing that and the area that we are prescribing on that XY plane is in fact has no restriction on y, it's only a restriction on x. That's a marginal probability, and we're saying that value has to be equal to the value under this kind of curve here, which is the marginal density. So this area has to be equal to this volume. And what that kind of means is that if you take all the volume in that on the right-hand side, what we have to do is somehow, if we squish that curve down, all of that stuff has to pile up on top of itself into a kind of like flat region here on the left. So what we're doing is really the same. Again, if now not thinking of this kind of like stripe, but think of like along a single line, right? If we want the value of the density at this point, x equals like, let's say -2 or something, right? We need to kind of count up along all the values where x in the joint where x equals -2 and y is whatever y is, and then add them all up. Except again, here we're not adding in the kind of usual discrete sense, but since these are continuous values, we need to add with the integral. And so but the intuition is the same as we were looking at in the discrete case where we're summing up along axes. Here, to get the value of the marginal density at a given point, we have to sum up or integrate over the joint density along a particular axis. So in this case, we're integrating out the y-axis. We're adding up along that axis.